Hi everyone, Parker Glynn-Adey here with Math 223, Activity 2 of Week 11. We've got some matrices here, and we're going to carefully step through the process of finding the image and the null space here. I just want to point out what is the image, right? So recall that the image of A is the span of the columns of A, right? So to use sort of the original definition, this is AV, where V is in Rn, right? So it's all of the outputs of our matrix, right? We multiply a vector by our matrix, and we get something in the image. Now, it turns out that this is equivalent to being the span of the columns. Another thing that I want to point out here is we've been given the RREF of our matrix, right? So we've got this RREF version that's equivalent to our original matrix A. And in that RREF, we can notice something interesting. Here's our leading ones, right? And in some sense, those leading ones span the columns, right? Every other column can be written as a linear combination of those first two columns. So what we're going to do is we're going to start looking for a basis for that image, assuming that the last two columns can be written as scalar multiples of the first two columns. So no, the first two columns okay. So we're going to see if we can do the same thing at the level of the original matrix and write these second two columns as linear combinations of our first two. Right, to see if we can get those guys to match up with what's going on in RREF. Okay, so we want to write 1, -1, -2 as being in the span of those first two vectors. If we look at the second, or sorry, if we look at the third entry here, we want to write it in the span of these guys, right? So we notice that we need to have a -2 going with that 1. Okay, now that's not going to quite match up, right? This would give us a -2 up top, which we don't have, right? 1 times -2 would give us -2. We need to get something positive up here, right? So what we're going to do is we're going to add on 3 copies of the second column. Okay, and if we do the arithmetic, this comes out as -2 plus 3, -4 plus 3, -2. Okay, good. So this worked out. That's excellent. Okay, notice how that relates to these guys here. We've got our -2 and our 3. Right, there's our -2 and our 3 coming up. Okay, so there's some kind of conjecture, some kind of relationship here. I want to see if that works for the next column. Okay, so we'll say 6, 7, 1, and we'll try that as being 3 copies of 1, 2, 1, and 5 copies of, oh no, sorry. Sorry, we want 1 copy of the first guy and 5 copies of the second guy. Okay, so let's see if that works out. We get 1, 2, 1 plus 5, 5, 0. And that gives us 6, 7, 1. Okay, so we got an equality there. Okay, so this is telling us that this notion of linear combinations is really working for us. And we can write these second columns as linear combinations of these first columns. Okay, so our basis for the span, or basis for the image, is the span of those first 2 guys. Okay, so just to step through the process there, again, our basis came from the places with leading 1s. Okay, we took those columns in our original matrix, and that gave us a basis for the image. Okay, very good. Let's move on to finding the basis for the null space now. Right, so the null space is all of those vectors v so that AV is 0. Okay, so what we want to do is we want to solve the homogeneous system obtained from A. Okay, so what we do is we start off with the matrix A, we reduce it to RREF, and then we get here. So we're looking at this RREF form, and we're sort of going to augment that with a bunch of zeros. Okay, and now we want to solve this, and this is finding the basic solutions. Right, we call them basic because they're sort of the simplest solutions, but they're also a basis for the null space. Okay, so what we do is we say that here are our parameters. right? X3 and X4 are parameters. Now we've got X1 is 2x3 minus x4. X2 is negative 3 x3 minus 5 x4. Okay, x3 is certainly just going to be x3. And x4 will be x4. Okay, so if we want to write this as a vector, right, we can say that we've got x3 copies of 2, negative 3, 1, 0, and x4 copies of negative 1, negative 5, 0, 1. Okay, so these are our basic solutions, and now we can say that the null space of A is the span of those two guys. Okay, very good. So there's our basis for the null space of A. Right, and this is exactly the same process as solving the basic solutions of a homogeneous system. Okay, so we'll calculate out the dimension of the image. So the dimension of the image of A is the dimension of span like this. Notice that these two vectors are non-parallel. Right? They're linearly independent. So the dimension of the span is going to be the number of vectors, which is 2. Okay, and when we look at our matrix, we want to calculate out its rank. And the rank of A is the number of leading ones. So I've got rank 2. Okay, so this dimension is, the dimension of the image is equal to the rank in this case. Okay, now we're going to move on. We're going to calculate out the dimension of the null space. Right, the dimension of the null space okay, we had exactly 2 vectors giving us that null space. Okay, we had the vectors right, let's work out the vectors again very quickly up at the top. Okay, so there's our solutions to the homogeneous system. So our span now is going to be as follows. Okay, again, these two vectors are non-parallel, right? They're non-parallel vectors. We've got two of them, so they span a plane. So the dimension is equal to the number of vectors. And notice something really cool here. These first two columns told us the dimension of the image. And these second two columns here told us the dimension of the null space. Okay, so very, very nifty sort of observation. The leading ones produce things that are a basis for the column space, and the parameters produce a basis for things that are the null space. Beautiful. Okay, now we're going to move on to proving this. This dimension theorem, by the way, is probably the nicest result in this whole class. I'm sort of honored to be proving it for you right now. It's one of these things that you're going to keep coming back to and back to. You know, the more math you take, the more this will seem deep and important. Okay. So let's explain why the dimension of the image is equal to the rank. Okay, so you have to explain in your own words. There's lots of different ways to explain this. I encourage you to take a moment now and just explain it to yourself. Try and write out an explanation based on what we've been doing in this video. Talk to a neighbor, talk to a Piazza, something like this, because expressing this yourself is much more important than hearing my explanation of it. Okay, so I would say the rank is the number of leading ones. All other columns of the matrix can be expressed as a linear combination of the columns containing the leading one. Okay, so once you've got the leading ones, every other column of your matrix can be expressed as a linear combination of those. Thus, every vector in the span of the columns can be expressed as a span of just those columns containing leading ones. Okay, so the basis given by columns of leading ones Okay, the basis given by the columns which contain leading ones in RREF is a basis for the span of the columns, which is the image of A. Okay, so right, so look back back to the first part of this activity, play around with that. We would absolutely love to hear your version of this on Piazza. So if you want to post this on Piazza and talk about it more, we'd be very curious to engage with you. But yeah, so there's an explanation for why the dimension of the image is equal to the rank. Okay, very good. Let's have a look at the next part. How do we find the number of basic solutions to AX equals 0? Okay, and how does this relate to the dimension of the null space? Right, so we find the basic solutions to AX equals 0 by solving for the parameters of the system. Right, so every leading one can be expressed using the columns containing parameters. Okay, so we first get the leading ones, then we move all the parameters over to the right-hand side, and that gives us a basis. So just as a quick little example, I want to show you what this looks like. Right, so if we're solving this homogeneous system, right, what we're doing is we're saying, okay, well, this is as follows. Now we convert this into a system of equations. Okay. This guy here corresponds to this leading one here and here. Okay, so when we solve, right, we get that xy or x1, x2 must look something like this. Right, or any multiple of this, so we could add a parameter there. So this entry, which was not a leading one, turned into this parameter. Okay, so every column containing leading one can be expressed as using the columns containing parameters. Okay, so these give us the basic solutions to the homogeneous system, and the basic solutions span the null space. Okay, so the number of basic solutions is the number of parameters is the dimension of the null space. Okay, absolutely wonderful. Again, this is just me explaining things, but if you would like to chat about this on Piazza, please do. We'd be happy to look at your comments or questions about this explanation. Okay, cool. Now we'll move on to the next part of the theorem. Explain in your own words why we must have this. Oh my gosh, this result is so nice. right? Absolutely lovely result. This thing just does so much stuff for us. So let's have a look at it. Let's look at it in one particular example and sort of see what's going on. Okay, let's just look at this matrix for a moment. Okay, here's our leading one. And here's our parameters. Okay. Okay, so notice that every column is contained in one of these categories, either your leading one or your parameter, right? So if we have a matrix that's m by n, then every column is either contributing to the dimension of the image or it's contributing to the dimension of the nullity. Okay, every leading one gives a basis element of the image. And every parameter gives something in the null space. Okay, when we add these things up, right, we get n. Okay, so it follows that the dimension of A plus the nullity of A must equal the number of variables or must equal the number of columns in our matrix. Okay, absolutely lovely theorem. As you continue your studies in math, you're going to keep encountering this idea over and over again. It's sort of like a core central idea, and I'm super duper happy that I was able to walk you through it. So congrats, you have proved the dimension theorem, which says that the dimension of the image plus the dimension of the nullity is the number of variables. Okay, if there's anything else that we can help with, please hit us up on Piazza, and good luck with the rest of your course.